Good morning. Do you able to see the presentation?
Yes, sir.
Okay, thank you. So let us start. So here it's a very rainy season. So I was just wondering if it is an offline class. So hardly we can manage to reach to the classrooms. But now in online, at least for today, I see that there is some advantage. Okay. Okay. So let us start. We are in module 5, machine independent translation, or sometimes called as the intermediate representation IR. We are working with that one. So we are continuing with the symbol table, and in the last few classes we discussed in detail regarding the symbol table, and specifically when the scope of the variable changes and it's a global, local, along with the compiler generated temporary variables, then how the entry differs in the symbol table that we have discussed. One thing was remaining, that if say there are definition of the variable inside a block only. Most of the time we used to avoid that one. Corresponding to each function, whatever is the local variable, we used to declare at the beginning of the function. Nevertheless, some programmer has a practice, and also we do not deny the fact that some programmer wish to define the loop variables for that loop only. So maybe some of you are familiar with writing for, instead of I equals to 0, you write int I equals to 0. Now the moment you do that one, then you are creating one instance of the identifier I, which is valid only for that block. By block, I used to mention that all the set of statements which are enclosed within opening and closing curly brace. There may be one statement, there may be more than one statement. But whatever is there, that is one block. So for example, this one, you can see on the left hand side, the program is very simple, because our intention is not to make the program complex, but to understand in different programming practices how the symbol table changes, or whether there will be any change in the symbol table or not. So in this case, you see that there is one global variable pointing here. Then there is only one function. Okay, it's a very simple function. It talks much about the nested blocks. As I mentioned, a block we are defining for the time being. Formally, we will define later when we will go for optimization. But for the time being, you can consider a list of or set of statements inside the opening and closing brace. So that way, one function itself is one block, because you know that function, so it's after the name of the function, the variable parameters. So you give opening curly brace, and then there is a closing curly brace at the end of the function. And as per my definition, as I said, that a set of statements which are inside the opening and closing curly brace is a block. So that way, a function is also a block. Now inside this function, t and u are local variables here. I am doing some assignment, t equals to x. X I am getting from the parameter int x. Next, I am giving one brace. This is opening and this is closing. Now you see that from programming point of view, perhaps without that we can work. But whenever we are giving that one, then this creates one block. And that block is nested inside the block of the function. And again, here there is a opening and here there is a closing. So here there is another block. So in that way, you can think that there are three blocks, two are nested. Okay, so this is, say, if I say 1, 2 and 3, three nested blocks are there. Now you keep an eye on this one. Inside the block 1, t and u are two variables which are declared. Of course, the function has a parameter x, and since my block 1 is the block of the function, so along with that local variable t and u, the parameter variable x will also go. Okay. Next, inside the second block, which is nested inside block 1, p, q and t, three variables are declared. Now, interesting fact, you noted that p and q, although is new, but t was already declared as a local variable inside block 1. I know you have done very good in programming and data structure, and I know you will say that t will have a separate value inside block 2 and it will be valid inside block 2 only. When it will come out of block 2, then it will get back its value which was in block 1. I completely agree with you, but why it is happening, and at the compiler level, how the compiler discriminate between the declaration of t or use of t after declaring that one inside block 2 and inside block 1, that is what we are going to discuss today. To finalize, or to actually conclude here, inside block 3 you see another definition of p. I declared int p and also I assigned p equals to 5. Now inside block 2 and inside block 3 there are two definitions of p. Okay. Now probably your previous teacher has mentioned during this block life span of the variable that the name doesn't mean anything except it is kind of an aliasing to the programmer. But compiler used to delete separately, specifically when it is nested. Because you know that if I take out this here, if I remove this opening brace and this closing brace and opening brace and closing brace, then you will agree with me that compiler will raise the flag because t and p are declaring twice. That is not allowed. Okay, but if I put this opening brace and closing brace, then it creates a new block inside the function block. So new block is, you can consider that kind of a new environment. That's why that is allowed. Now what do I mean by this environment? Environment means it will create one symbol table corresponding to each block. Now see that if say you give one opening brace and closing brace, for example, you know that for if else statement also, or switch case or any loop statements for do while or while. Not necessarily, not every programmer declare a new variable or reuse another variable, declare a new variable with the same or different name inside that block. Because you know, in if else, in for loop, while loop, do while loop, in switch statement, there is opening and closing braces. So it creates a block. Now, if there is no new declaration of the variable, then there is no need of symbol table. But whenever there is a new variable declared, the name wise that may be same as previous one, but new declaration when it is, then corresponding to that block, one symbol table will be created. Now you remember from our previous discussions that in the symbol table on top there is this provision that I can mention who is going to be the parent of this symbol table. So for global, st.global here, parent is null, nobody is the parent of the global, and currently only the global variable a of data type integer, global 4 is the size, and the function f which takes one integer as an input and outputs int, so int to int mapping function doesn't consume any space, is there in the global symbol table. You can see that I have incorporated one more column for one more attribute which will contain the information that this particular, if it is a function or say block, then what is the name of its symbol table. You remember that I mentioned that when say I am at the lexical analysis stage, then I need to store only the name of the identifier, what is your location, what is its location. After that one, as I keep on progressing, say after that say parsing, then semantic analysis, and this IR, then we will go to code generation, etc. Then more and more information may be required to enter in the symbol table. So when say you are moving, say in laboratory, you are moving from assignment 3 to 4 to 5, then I understand since it's your learning phase, so at the beginning you are not getting the holistic idea. That's why what we will do, say when assignment 4 will be released, we will mention that for these reasons, if some improvisation is required to do in your assignment 3, please do that one and then integrate that one with your assignment 4. But when you will have the holistic idea, then at the beginning itself, you know that how many attributes or fields are required for symbol table. But for the time being, let us keep on adding the columns whenever it is required. Now for the time being, the requirement is that keep an information corresponding to each function that what is its symbol table. So it is st.f. So what is in st.f? Of course, the parameter will be there, that is my x int parameter. Since it's integer, so 4 bytes, I am assuming starting from 0, and then it is not linking to any symbol table, so it's null. Then tu are local variables. Okay, integer type local variable 4, accordingly offset is adjusted, no linking. Next, you see this is interesting. So next, what is happening in st.f, you have seen that there is a block here. Now how do I store the information corresponding to that block? Again, I mentioned that inside this block, if no variables are declared, then I may skip this one. And as of now, up to this, or up to the last class actually, we didn't mention anything to have some information corresponding to this block. But now it is required because new variables are declared here. By new, I didn't mention always that new name. It can be the same name, but new declaration. So as if I am assuming that this is nothing but one function whose scope is inside the function f. You will all agree with me, right? So I am giving a name of that function. Look, this is not a function, of course, I understand. But as if this is a function and I am storing that information. So what I will do, so I can use some convention to give the name. Here I am using the convention that f is the name of my function. So f underscore data type is null, and its type is, it is not actually function, it is a block that you mentioned here, block. There is no memory requirement, there is no question of offset, but it stores the information that for f underscore 1 block, what is the symbol table. Okay, so I will go to that symbol table here. And for this st.f, who is the parent of this symbol table? That is the st.global. Now in st.f1, so st means symbol table dot f1 because I gave the name f1 for this block. First, who is its parent? Of course, st.f here. Now inside this one, who are the local variables? pqt, all are local variables. They are integer, so 4 bytes, accordingly offset is adjusted. Now you see one more difference of this block with respect to function. For block, I did not have any parameter, so that variable is absent here. Next, what I see that inside this block, again there is another block here, block 3. So similar to the previous one, I use the same convention. So the name of this block I mentioned f underscore 1. Since it is inside, so I am giving f underscore 1 underscore 1, and the corresponding symbol table is st dot f underscore 1 underscore 1. And for this symbol table, only local variable is p. I am making an entry for that. Now look, the convention I am using that if it is nested, then I will append underscore 1. So f underscore 1 I added. Next f underscore 1 underscore 1 I did. Now if it is the case that third block is not nested inside block 2, but it is separate. Say for example, it was the second block. This is my second block, and this is my third block. If this is my situation, then I will not write this. I will write say f underscore 2. That is the convention I am using. Okay, and similar to the way I generated say t1, t2, t3, which are the temporary variables generated by the compiler, for this name also, what I can do, it is name of the function that I have stored here as f. Along with that one, I will concatenate underscore, and then I will write one integer in order to generate the new name for that particular block. Of course, I am keeping one counter so that I can keep on incrementing 1, 2, etc. And if I identify that it is a nested block, then instead of incrementing this one, then f underscore 1 or say f underscore %d underscore followed by another %d for another say block, it will be there. That way I'll keep on generating the names. So to remind you, for the temporary we did t %d. This was printed using sprintf so that I can store that as a string. String means that will be the name of the variable t1, t2, and this %d is the name of one variable which is declared as static, and I will keep on incrementing that one. Okay. Now corresponding to this, 3 address code is here. It will be pretty simple. T equals to x. So let me erase everything. Yes. So t equals to x, it is coming directly here. Now for p equals to a, so p, so what I am writing, so p @ f underscore 1, which means p which is declared inside f underscore 1 block is equals to a underscore a @ global. So this @ global to indicate that this is actually this a global variable. Now regarding this @, you may have different notation. But the point is, you have to discriminate them, and at the same time, you see when I write p @ f underscore 1, then I have the knowledge that f underscore 1 is one block and p is inside that block. Okay, if you keep those informations with you, then during the semantic analysis, it will be easy, and there is a less to no chance that during compilation you will lose some meaning or logic. At any cost, I should not lose the actual meaning of the program due to compilation. If I do that one, say either during say IR generation or code optimization or any phase, then your compiler is not correct. Okay. Now the same block, when it is flattened, okay, so then you will see that the scope is here, t equals to x. This was the case, and when they are flattened, then accordingly the table has changed here, that you can see. I am not going into details of this, you can read this. If you have any question, definitely you can ask me now or later also, that's not a problem. Now in this case, we are trying to emphasize the global function scope for add and main. So in this case, you see that the variable x, array y are declared globally, and int add, this is the function declaration of the add, that is also global. Variable a and b double type, that is also global, and function int add void main, that is also global. So in my global symbol table whose parent is null, what will be entered? First x I am encountering during the scanning, so x will be entered first, followed by AR, then Y, then add function declaration, then A, then B. Now for this add, no more insertion is required because function is already declared, and corresponding to that it is entered. And next main will be entered. Accordingly, their types, their category, their size, offset, and link to the symbol table is also entered here. Okay. Now, before going to this symbol table part, if I look at the 3 address code, then you see in the add there is int t, t equals to x plus y. Now here t has 1 indicates that it is local variable. Sorry, it is compiler generated variable. T has 1. And x and y is added and assigned to that t has 1. Then t has 1 is assigned to t and return t. That is my function add. Now again you see that since I have one programmer defined variable t, so I might be confused if I also use the same convention like t1, t2, t3 for compiler generated temporaries. So to avoid that one, the naming convention used is t has 1. So it is entirely up to you. Definitely, the name of your compiler generated temporary should be following the rule of the identifier. But inside the identifier, you may have some name which is very uncommon and you are more or less certain that programmer is not going to give that as the name of the variable or say name of the function. Okay. Now for function main, t has equals to 1 because of this one. Then x is assigned to t has. Then t has 2 equals to, so here ARX x is there. So this is two-dimensional array of size 2 cross 3. Now you know the rule. Assuming integer is of size 4, so 4 multiplied with 3, that is 12. 12 multiplied with x, that is my index, I am getting t2. And 4 multiplied with x, I am getting t3. Now t4 is t has 2 plus t has 3 and y equals to AR, t has 4. And when I am calling the function, it is basically add x comma y. So parameter x, parameter y, call add with 2 as the number of parameters. It will return C and finally return. Now again here you see that which we also demonstrated on the last class, that this t has 1 equals to x plus y followed by t equals to has 1. You may write that one at this 3 address code generation. There is no problem with that one. But during machine independent optimization and p-fold optimization specifically, that will be changed to t equals to x plus y. And that way, we will reduce some compiler generated temporary variables also. Now accordingly, the symbol table is generated. I believe this is very straightforward, so I am not going in detailing this one. Next interesting part is when it is global and declared in some other file. Going back to the previous slide, you see that there are 5 global variables: x, array, AR, y, a and b. But everything is inside one file. Now if I believe some of you or everybody has done multi-file programming, and if you are doing that one, then you see that there is one file whose name is global.c. Inside that one variable is declared, int in equals to 5. And since it is declared outside of any function, so its scope is going to be kind of a global. And in file main.c, capital main, capital M, this is the content of the main.c. So there are two files, file 1 and file 2. So file 1 and file 2. In file 1, there is a use of variable n, where here. And this n is the same n which is declared and assigned in the file global.c. Now how the compiler will know that this n here is declared somewhere else? Because you know by this time, at least when you have done your assignment 2, during the make file and also in the assignment 1 that I can compile the C file. And when I will compile the C file, the object file will be generated. Now, if I just compile, then the compilation will be done on each .c file. So main.c can be compiled independent of global.c. Now, unless otherwise you are linking them or you are connecting them in some way, then it is not possible for the compiler to understand whether this n is declared somewhere or this n is a mistake because you are using that one without declaring that one. That's why what you did or what you used to do is that you mention extern int n, indicating int n is one variable which is declared and possibly used or assigned in some other file. Now looking at this, compiler will be relieved. Okay, so it is declared somewhere else. With that information or assumption, let us compile main.c and generate the object file. Now it is the responsibility of the linking process and of course who are building the executable file to link all those files where there is a dependency, because main.c has dependency on global.c because the variable n is declared and assigned in global.c but used in main.c. So that will take place during the linking process. During the linking process, if n is not available, then it will generate a linking problem. So keeping that in mind, when say compiler is compiling, then what it will do that in st.global for function main.c, of course, it will write in as integer and its type is extern, which means it is declared externally in some other file. Definitely the size will be 4 and offset is 0408. Now for the sum, it is integer to integer function. For sum, so two sum. So you please note it down. One is sum with capital S, that is the name of the function. Another is sum, all small, that is the global variable int, that is of type global. And of course main is there, void to void, it's a function. Along with that one, I have the separate symbol table for sum function and main function. So for sum function, inside I see LCL STC sum is the name of one variable, its integer and data type is static. So LCL STC sum integer data type is static, 4 bytes, and accordingly offset is adjusted. But the first integer sum is its parameter, that is x integer, and it is of parameter type. Inside the void main, it is the a variable only, it is integer and that is local variable. Now based upon the fact that whether you are integrating global.c during the compilation or separately you are compiling, this symbol table may be generated along with this or may be generated separately. Say if it is the case that you wrote only one, so separate global.c and compiling separately, then when you are compiling that one, then this symbol table will be generated. Its symbol table will be there. Separately, symbol table for main.c, st dot sum, st dot, and when I will link them, then it will be compiled. Okay. So 3 address code is pretty simple that you can see. I'm not going to explain that one. Okay. So here corresponding to LCS equals to x, So before that one, so actually LCL STCC sum equals to 0. That is the first thing. Next, it is the increment operation. So plus x. Then it will return LCL STC sum. For this, after this, for the global sum equals to -1. Then a equals to global underscore n in order to differentiate this n with any other n if there is any, because this n is global. Then a is the parameter, and with that parameter you are calling function sum, only one parameter. And then a equals to a multiplied with a, again with a parameter, you are calling function sum with one parameter, and finally you are returning. Okay. Now here is an example of the binary search. In this case, you can see that the declaration of the variable is not blockwise. So it's only the parameters array A, integer L, integer R, integer V. That is the information. So symbol table global, just based upon this function, if I build, will have this function related information. So BS function array star A cross int cross int cross int maps to int. It's a function 0, 0. And corresponding to this BS symbol table, so parameter A, that is array integer, then L integer parameter, R integer parameter. Sorry, there is a duplicate entry here. So L, R, after that it will be V. This will be V. Sorry, there is a duplicate entry V. And after that, this local variable int m. Okay, so one local variable is there. So that variable is declared here. That is local. Now, one thing you can think actually, inside the function, it is not the declaration of m. M is declared inside one block inside the function. So that way, I may think that, okay, there is one block, and accordingly, in this .bs, I can make an entry of say bs underscore 1, and then in bs underscore 1 corresponding to this block, I can have say m, then all the temporary variables which are required for this 3 address code generation. That is one case. Another case is that, okay, since there is only one loop, and that is all about this function, so I am ignoring. But if you are say implementing one program, then I am sure that in your program it will actually make an entry after this V, it will make an entry of bs underscore 1, and that will say that bs underscore 1 dot st dot this, there is one symbol table. So starting from this m to everything will be inside that symbol table. Okay. Now this is about this symbol table thing, but one more interesting feature is here when I am converting that to 3 address code. Definitely the 3 address code is pretty simple. There is a while loop. So what you are doing, so if L less than equals to R, go to 102. This is the else part, you need not have to write. If you are not jumping to 102, then you will go to 121. Then L plus R, you are computing and storing in compiler generated temporary T1. Then T1 divided by 2, storing in T2. Then you are assigning to M. Then M multiplied with 4, that is in T3. Then AT3 equals to T4. Then if T4 equals to V, this condition is being tested here. Then you are going to 109. If you are not jumping to 109, you will definitely come here. Then unconditionally you will jump to 111, and it goes on. Now the interesting fact is that 3 address code is fine. But say when I am say generating the 3 address code, so I am looking at this code and L plus R, sorry, even before that, L less than equals to R, I tested. After the testing, I know that there will be branch, true branch, false branch. So if it is true, then go to. If it is false, then go to. Now, as long as I am writing, say, L1 or L2, I don't have any confusion, because it is L1 level, it is L2 level. But say when I am placing 100, 101, so you see this is actually the index, and at each position there is one 3 address code placed, that you can see 100, 101, 102 up to say 122, this way. Now my question is that how do I know that when I will compare L less than equals to R, go to is fine. If I give some level, say L1, and I'll keep on incrementing the level, say L1, L2, L3, that is also fine. How do I know? I have to go to 102, in which 3 address code I need to jump. How do I know when I am at this position for generating the 3 address code? Okay, if I assume that, okay, so this is my true case, so there will be a jump statement just right after this one at the 101 place. So definitely my true statements, if there is any, will start from 102. That way you can think, okay, so it will be 102. Fine, I agree, kind of. But how do I know that this go to will be 121? Unless otherwise I generate all the 3 address code, how do I know that how many 3 address codes will be generated corresponding to the true case for that condition? Because unless those are exhausted, I cannot get a scope or place for writing my false statements. False statement means the list of statements which will be invoked or called if the condition is false. If you think, then you will find that it is true for almost all condition testing. And it is true. In this case, I looked at the 3 address code, and after all the generations are done, then only I am writing this 121 or 102. Because without generating the 3 address code, all the 3 address codes, it is not possible. At least up to which we have discussed, based upon that one, it is not possible. Then you may think, okay, one solution may be that I will make it L1, L2, L3, or I will keep it blank, and after the generation is done, then I will come back again and I will fill it up. Might be that is possible. But we will see some more intelligent way through which we can able to handle this one. That will come later. Okay, but here we identified one problem which is definitely not related to the symbol table. It is mostly the part of the 3 address code generation, that when, so for the assignment statement or arithmetic expression, this kind of problem will not arise. It will arise only when there is a go to statement, or based upon some condition I wish to make some jump. Then jump to where? So definitely if it is a jump to backside, say I am jumping from say go to 100, then it might not be a problem. But jumping forward with an estimate that how many instructions will be placed next is not possible. Okay. Now this is the final example for the symbol table. It is a simple program for taking the transpose of a matrix. I'm not going in detail discussion. It's very simple. If you follow all the discussions, then you can able to figure out. Okay. So you go through this one. If you have any question, definitely you can talk to me. But I believe this is very trivial. Only thing is that, yes, I agree that go to 108. How do I know standing at the position 103? Go to 134. How do I know standing at 104? Better if I write say L1, L2 that way, then it is fine. But this 108 and 134, again this first column indicates the serial or sequential number corresponding to each 3 address code. So that when I will say go to 134, then it makes sense. That makes sense, but how do I know it is 134 or 108? As of now, we didn't discuss that one. We will discuss that later. But keeping that aside, rest of the 3 address code generation or symbol table generation, I believe you can able to understand that one because we have done several examples with that one. Okay. Now let us move on to handling arithmetic expressions. Grammar is very simple. It is the previous grammar, but ambiguity is there. That's not a problem. On the last class of our module 4, we demonstrated that one, that Bison has the capability to provide the precedence and associativity information along with the grammar. So for production rule number 4, 5, 6, 7, although they look alike and sometimes there may be some conflict over the whether to shift or reduce, that will not come if I follow the precedence or associativity information which is there in the Bison. Now for this calculator grammar, whatever we have discussed on top of that one, excuse me, we need few more information. Grossly, again if I go back to the previous slide, grossly you can differentiate this into 3 parts. One is E, which stands for expression, another is ID, which stands for identifier, another is num, which stands for some constants, so integer constant or floating point constant, right? So S is statement, L is the long statements. So except that ls, and you know that slashing is the new line. So except that L and S, so this identifier, num and expression requires separate attention. Why? Because identifier means that some location is required, some value it will store. Num indicates its integer or floating point constant. So it will also, this integer or floating point constant will also have some value and I need to store that one. And of course, when it is an expression, okay, now from third production rule, you can see that expression I am assigning to identifier. So this is also similar to the identifier. That's why location is required for identifier as well as for E. So E.lock is the locations to store the value of the expression. This will exist in the symbol table. ID.lock is also the location to store the value of the identifier ID. This will exist in the symbol table. Now you see that again, as I mentioned, that we started with the lexical analysis process. Then in the symbol table, the requirement was that to just enter the identifier and return the address or location of that identifier. Now as I proceed, then the symbol table is becoming enriched. Now here I am suggesting to add some attribute and that will exist in the symbol table. Finally, the num.val is the value of the, although here it is mentioned integer, but definitely you can extend for the floating point. So basically it is the numeric constant. So those 3 attributes are required. Now at this stage for generating the IR. And functions, 2 functions, although I mentioned auxiliary methods, but is required for generating the 3 address code. If you remember correctly, that when last time we discussed about the Bison in the context of the LALR parser, then we mentioned $, equals to $1 plus $3 when the production rule is E drives E plus E. Now I was evaluating that one, and we also demonstrated with a stack some expression that was evaluated. A equals to 8 plus 9 slash n, a plus 4 slash n, it was there, and final output was 21. We discussed that one. Now my job is not to evaluate that one, but to generate the 3 address code corresponding to that rule. So I am incorporating two functions. GenTemp, it will generate a new temporary and inserts it in the symbol table, returns a pointer to the new entry in the symbol table, and emit, it will spit or print a 3 address code of the form result equals to arg1 of arg2. We are familiar with this format, that is the format of the 3 address code. When 2 arguments are there, and op indicates a binary opcode or binary operator. But if it is a unary operator, then arg1 will be missing. And if arg1 and op both are missing, then it will be just a copy statement. So 3 attributes: e.lock, the location information for the expression; id.lock, the location information for the identifier; num.value, the value information of the num, the numeric constant; and 2 auxiliary functions, gentemp and emit, one for generating a new temporary and another for splitting or printing a 3 address code is required. With this one, we will generate the 3 address code instead of evaluating that one. Of course, if you need to check the correctness of your generation, then from that 3 address code you can evaluate and get that data. But what I am trying to say, that if you generate the 3 address code, and as I mentioned earlier also, corresponding to each 3 address code, if you have a set of machine level instructions, so you can substitute that machine level instruction at this 3 address code position. Then the machine, you give it to the machine, and the machine can be able to evaluate that one, that a equals to 9 plus 8, or sorry, a equals to 8 plus 9, that can be evaluated by the machine. Okay, so that we will go. So before that, let us take a small break for 5 minutes. So we will be back at 9 o'clock. If you have any question, you can ask me right now, or later also after the break. It's up to you. Okay, so we will resume at 9 o'clock. So, do you have any question as of what we have discussed? Okay, then continue this arithmetic expression part. Now, if I add those attribute information and the function information along with the expression grammar and call them as the actions, then the modifications are here. So there are 11 production rules. For the first two, L derives ls/n and L derives s/n. There is no action related to this emit or generate or any attribute that we mentioned. Now, when it is s derives id equals to e, then you understand that the content of the e is supposed to be assigned to id. So what I am suggesting that this is a copy statement in 3 address code. So the content which is in e.lock will be copied to id.lock. So this is just a copy statement. Now for the production rule 4 through 7, 4, 5, 6, 7, it is same except the operator is different. So let me explain the first one, 4, then rest will follow. So the production rule suggests E derives E plus E. As I mentioned, the subscript 1 and 2 indicates two different instances, but at the grammar level, all are non-terminal E. E1 indicates it is one expression, E2 indicates it is another expression, and E indicates it is another one. Now you will also agree that if two expressions are given to you and you need to add them, then after the addition you need to store in some place. So you need to create own memory location. That's why I will call first that gentemp, which will create one temporary location. Now in the context of the 3 address code, this is similar to creating compiler generated temporary variables. So in this temporary variable e.lock, I am supposed to store the summed result of E1 and E2. So first what I did, I generate e.lock equals to gentemp. Then my 3 address code is e.lock equals to e1.lock plus e2.lock. So at the location of E2, what is the value? With that, at the location of E1, what is the value will be added and the result will be stored in e.lock. Perfect. I am emitting that one. What does that emit means? Spitting or printing. Showing you the previous slide here. So emit is spitting a 3 address code of the form result equals to arg1 of arg2. And gentemp generates a new temporary variable and insert it in the symbol table, similar to compiler generated temporaries. Details of these two functions I will come shortly. But actions first. Similar to this production rule 4, 5, 6, 7 all will be same, except their operators are different. Okay. Now at the action level for the production rule 7, I am not checking the division by 0. But you remember that in the parser, in the bison, when we are implementing, then we are checking that whether e2.lock equals to 0 or not. If yes, then we raise the flag division by 0 error, otherwise we perform the division. Okay. Now production rule 8 is interesting because the content of u1.lock is basically assigned and there is no such change. Now here one note is given, no new temporary, no code. Why? Because you see that although E derives within parentheses U1, but its role is that just to change the precedence of the operation. As such, it is not a copy statement or no operations are performed. So only thing you will have is that after the execution, the parenthesis will be removed. That's it. So there is no requirement of any temporary variables, and also no code is required. Although I am telling that u1 e.log equals to u1.log, but actually it is e1.log, the same variable. Since the same variable is being used, even copy is not required. But for third production rule, I do not need any new variable because id is already there, and right hand side e is also already there. But it is a copy statement, so code is there. That code I am emitting. So this is emitting. So all emitting indicates that there is a 3 address code. But for this 8th production rule, no code, no emitting also. Okay, only the parenthesis will be erased or removed. But for production rule 9, I need new variable and corresponding 3 address code, because E1 is having some value and E is basically negation of the E1. So first I generate one temporary variable c.log. That will be, when translated in 3 address code, will be something, say t something, that I will again come. Now I limit e.log equals to minus u1.log. So the difference, you please note, between 8 and 9 is that for 8 only the parentheses will be removed, but for 9 u1 and e both are different as per their value. So I need a separate memory location to store that value. Next, for e derives num, e.log equals to gen10, and emit e.log equals to num.value. So again, new location is generated because on the left hand side what is there is not available. So I am generating some temporary value. Inside that one, I am copying the value num.value. Now e derives id. Again, I am excuse me. So no code is required, no new temporaries are required, because id.log can be used directly for this purpose. Now regarding this emission, so 2 different variations are possible. One is that spit or emit as soon as I encounter that particular production rule, or you store that one in your program, and once everything is done, then you print or spit. So for the first case, no extra thing is required apart from this what we have discussed so far. But for the second case, each 3 address code needs to be stored in some array, and once everything is over, you just print the array of 3 address codes. Okay. So there are little variations in that one. We will discuss that one later, but these 2 are the variations. Now in the translation, what will be the change right now? So corresponding to a equals to 2 plus 3 multiplied with 4, what is given here, you know what will be the 3 address code by this discussion. So t, say temporary, if I name at 00, t00 will be 2, t01 will be 3, t02 will be 4. Then t01 multiplied with t02 will be t03. Then t00 plus t03 will be t04. Then a equals to t04. Now if I look at the tree structure, then this tree structure was known to us. So starting from, say, L using a top down, or say starting from the expression equals to 2 plus 3 multiplied with 4 using bottom up, we can get this one. Now, because of this emit, gentemp, and say other attribute information, extra thing which will be added is id.log is a now here. Instead of say num, it will be num.val, that is 2, and here it is cut, actually it is num.val equals to 3, here num.val equals to 4. Now when it will be reduced to e, then I know that corresponding to this e, if I go to the previous slide, e derives num says you generate one temporary location and emit e.log equals to num.val. So coming back here, so e.log equals to num.val, and that is my temporary t00. Next, this is my temporary t01. Next, this is my temporary t02. And after the multiplication, t03 is my temporary. Then after the addition, t04 is my temporary. And a equals to this t04. Next, I will reduce to L. Okay. Now, what is the modification in Python specification? So I am just pointing out the modification what is done based upon the discussion just now we have on top of the existing Python program. So you remember that this is indicating the precedence and the associativity information, this part. The expression is here. Simp and int value discussed. This is the symbol table information. This is the symbol table information. This is the union operation. This statement, there is no change. Statement list or statement. Now it starts from here. When name, basically it is id equals to expression. Id equals to expression. So if it is the situation, then you remember emit was just a copy statement. So $1 pointer to name equals to $3 pointer to name. I will emit that information. And for that you remember that since id location is already there, I need not have to generate any temporary variable. But for production rule, addition, multiplication, subtraction and division, I need to generate the temporary variable. So for addition, I am explaining first here. So previously, if you remember, after expression plus expression, it was $$ equals to $1 plus $3. Now, my action is $$ equals to gentemp. I am generating a new variable. Again, the details of emit and gentemp I will come shortly. Just you can think that gentemp will generate a new memory location. It will insert that in the symbol table like the temporary variable t0, t1, t2, and it will return that address to $. Then emit $name, comma $1. So this $, name is my result. This is my 3 address code. So $1 is my argument 1. This addition is my opcode, binary opcode addition. $3 name is my argument 2. Okay. Now the same thing is repeating for subtraction, multiplication, for division. Although in this case that checking on $3 is missing, but definitely you can add that one. Now for negation, so it is the same thing, minus expression percent u minus. Now you see the situation here. So when you are doing say lexical analysis, then your minus has come just as a punctuator. Now based upon the context, whether it is in between two arguments or in front of some argument, whether it will be interpreted as a say binary operator or unary minus, or when say it is part of the identifier, then how it will be interpreted, that will be added. Now this $$gmtemp and then $name, $to name, and this minus. So that is the 3 address code for unary minus operation. Okay, then name, number. So when say you are equating with the ID value, and this is also that name, number, it is given. Okay. Now looking at the two functions that I mentioned. So first of all, here, this is my symbol table. Small changes here. Initially, it was simlook. I was searching for the existence of a variable identifier name, either it's variable or function. If not, then I am returning it is not there, or I was making an entry of that new name and then returning that pointer there. Of course, there should be an error message because you are assuming finite number of variables you are creating, but if more is required, then since you are implementing with a static array, so there should be a limit, and for that you are giving this one. Now two functions which are added is gentemp and emit. Gentemp first, as I mentioned, that this will generate the compiler generated temporary. So this will generate some variables. Since it is generated by the compiler, so its name is compiler generated temporaries. The programmer has nothing to do with this one. It is entirely compiler's responsibility, or you, when you are designing the compiler, your responsibility to keep track of these temporary variables and do not mix with the programmer defined variables. I believe as of now you understand the sole purpose of this temporary variable is to break the complex statements into simple statements so that each simple statement can be represented by a 3 address code, because corresponding to each 3 address code I may have a list of machine language, so that my translation from the 3 address code to machine code will be very easy. Okay, so what I am doing, you see, probably you already figured out when I was showing you the name of the compiler generated temporaries, that first I have static int equals to 0. That is the counter which is attached. And the good thing is that by changing this integer variable only, you can generate a number of variables. And since you do not know a priori that how many temporaries you need to generate, because compiler is one, source program varies. So you should have a provision of such thing like some integer variable. Otherwise, if you say think A, B, C, D will be my list of variables, then you will be exhausted sometime. Means all the variables will be taken, then also you need some more extra variable. So it is difficult to manage. Now in the name of the temporary variable, so character string 10, and this sprintf, perhaps you know the function, it takes 3 arguments. So first argument is the name of the string, and next is the format of the string, and then finally what it will write. Actually this is the printf, but if it is a printf, you know the format of the printf. There are arguments inside is the first format of the printf, followed by the variables which will be printed, and by default printf will go to the terminal. But if it is sprintf, the same thing, printf, instead of going to the terminal, it will print to some string which is given as the first argument to this sprintf, that is my str. So by this way I will create one temporary variable, and you know that since it is a static, so at the first occurrence, or first when I will encounter this function or invoke this function for the first time, then C will be 0 assigned, but after that one, it will return its previous value. So one increment is enough, and that is what I did here. So after this, it will return simlook str. Why simlook str? Because in the simlook, it not only searches for the existence of a variable, but if that variable is not present, it will enter and return the address of that variable. So that's why simlook. So in the return, it is just a function call. It is not returning directly. It is a function call to simlook, and it is returning. Few lines, but very powerful one, this gentle. Now in the emit, as you understand, there will be 4 arguments. 1 for the operator, 1 for the result, 2 for the arguments. Now there is a provision that argument 2 may be absent for unary operation, or based upon your implementation, you may think that argument 1 is absent but 2 is not. That is your implementation. But my point is that only 1 argument will be present for unary operator, and 1 argument and 1 operator both will be missing for the copy operation. So keeping both the options open, so if S3 is null, then, so this statement says that if S3 is not null, then here, but if S3 is null, then there is a possibility that either it is a copy statement or it is a unary operation. So here C indicates that it is an unary operation. So printf s equals to, this is unary operation here, %c followed by my only 1 argument, and this is my result. If it is not even unary operation, then it is just a simple assignment statement. So %s equals to %s. So I am emitting that one. So this S1 and S2 are the string name of the variables or the identifier that will come. And if it is S3 is not null, then it is a standard tree address code containing result equals to argument 1 operator argument 2. So that is the tree address code. Now this is fine, but considering the fact whether it will be a lazy splitting or immediate splitting, means once I will generate, whether I will throw it to the terminal or set to some file, or I will store it. Once all the generation of the tree address code is done, then I will print. For that, in the parent function from where I call this image, I need to maintain one array of strings where each index will indicate one tree address code, and tree address code is where either this one or this one or this one. So these 3 are the 3 different tree address codes which will be emitted. And by looking at this content, you see that this is nothing but a string of, or a sequence of characters, or a string. So that's why I said that you need to store an array of strings or an array of character sequences. Okay, so these 2 functions are new, and I explained that one. This YY error and main is same, so it's fine. I am not going to discuss. Header file y.tab.h, there is absolutely no change. Just for your information, it is placed here. For the parsert.h, yes, I need to include the information that I have one gentemp function whose type is symbol table, and I have one emit function. So here it is mentioned void because I am printing. So it is an immediate split. But if I wish to store that information, then perhaps I have to change this emit to character start, so that instead of printing, it will store that in some string and return that string, or it will store that in some array of characters and it will return that array of characters. So these 2 are the only changes here in the parsert.h file. Flex program, there is no change. it will remain same. Now you see that as we are proceeding, then the same Bison, Flex, their header files, we are discussing that what are the extra thing we are adding. So that way we are putting more and more information. So at the beginning, you have probably seen, some of you pointed out and sent me email that this is not available, this is not available, it is not supported. Yes, that's true. There are two reasons. One, we are not working with the complete C program. It is the tiny C, a subset of the C program. And also, time to time, we will keep on adding the information because not everything is done at the, say, scanning or lexical analysis stage. It will come one after another. But in this case, Flex specification wise, there is no change. Now this is the sample run, and you can go through this one. I am not going into details here. So the same Bison program which we just discussed, based upon that Bison program, so it was a print statement from the init. So whenever we will type, say, equals to 2 plus 3 multiplied with 4, then it will print T00 equals to 2, T01 equals to 3, T01 equals to 4. This it will print. When we will say this 3 address code will be generated. When we will give this 3 address code will be generated. So these are the test cases corresponding to the Bison program, which includes the attributes e.lock, id.lock, num.val, and two functions, init and gentemp. Gentemp is responsible for generating these names T00, T01, T02, and init is responsible for printing each line of this code, which is nothing but the 3 address code. Now, if I quickly go through this handling of equals to 2 plus 3 multiplied with 4, because we already discussed in detail, then when I will say this ID, it will be pushed into the stack. And also, since I see one identifier, it will be in the symbol table. Now this equals to will come, then num will come, and num is actually 2. This is num. After this num, so it will be changed to E. So from num to E using the production rule. This one number is not mentioned here. Okay, fine. Now when it is E, now you see that it is expression. So using gentemp, I generate one temporary file T00. So this T00 is entered in the symbol table. Next addition, for the shift num, again because of this num 3, so I will generate E, and because of this E, T01 will be entered in the symbol table. Okay. Next, T01 up to was entered, then multiplication that was in here, pushed here, then num, because of this num4, so it will be converted to E, because of this E, T02 and T02 is entered in the symbol table. Now the multiplication will take place, E multiplied with E, and for that I need to generate one more temporary file to store that information, that is my T03. So T03 is entered here. And the opcode, if you remember, will be T03 equals to T01 multiplied with T02. Okay. Next, T01, T03. So after this one, I need to add these two, and after the addition, I will place them. And finally, this is the number, my symbol table, and this is my stack position. Okay. So finally, this is the total final result that you can see here, and corresponding to that, the 3 address code. Going back, let me go back here. That we have generated. Okay. For the addition, T04 will be created. So I think it is not showing here for the addition. Yes. So this 3, after this 3, here T01 and T02, it will be created, and this is not T00, this will be T04. And here there was T02, T03, then here T04 extra will come here, and here T04 will be there. This T04 is coming from here. So that is it, and here there are further expressions for the handling. This is one famous one we discussed in detail in the context of the parsing. So you can see that one. Only thing is that extra that actions for generating the 3 address code, that will be added here. Okay. Other than that, it is the same one. Now this is the translation I was talking about, lazy splitting. So whatever I have shown you that based upon the printf statement. So as soon as I encounter one expression, just following the precedence and the associativity, you print that one. In case of lazy splitting, so it will store each of the 3 address code in some array, and once the conversion is over to 3 address code, then it will print. Okay, so intermediate 3 address codes are formed as quads and stored in an array. The quads are split at the end of the output. This can help optimization later. So we need to have one class definition if you are writing in C++. If you are writing in C, accordingly you can modify your program. So in the string, what you need to store, opcode specifies the 3 address instruction, argument 1 and 2 both are character star, and the result, that is also character star, because argument 1, 2 and result is the name of the identifier. Whereas opcode, I am telling opcode type, which means I have in my mind, or my intention is to define one opcode type which will have the positive, negative, subtraction, addition, all those informations. I'm going to that. Okay. Now, as I mentioned here, the major difference. So you can see that first thing here, I am defining one array to store all my quad arrays, Q array, and the data type I am calling as quad. What will be the content of the data type? Going to previous slide, op, argument 1, argument 2, result. Now int quad pointer, just to keep track of how many entries are there in the quad array. So these two are modifications, and you know in Bison specification calc.c, the same program, this part is for the C declaration and definition. So I am having that here. There is no change up to here. But when I am reducing to the start state, then what I am doing, you see that I am printing all the quad arrays. And that is the only place of the printing. On the right hand side here, you will see no printing statement. On the previous case, when I demonstrated Bison, corresponding to each action, there was emit, and emit means printing. Now I am not printing that one at each step, rather I am storing. Regarding the storing, I will come later. But printing is only here when I am reducing to the start state, which means I accepted everything and I am going to the start state. Then I will print everything one after another using this for loop. Okay. Now here a statement name equals to expression. Now you see quad array, quad pointer. So from here, new quad copy comma $name $3 name. This is my copy statement. And new quad, so you know that this is written in C++. So I am creating new object. Using the new, I am creating one object, this quad. Regarding quad class, I will come in the next slide. Similar to that, $gentemp, then I am adding Q array equals to new quad plus What is plus? Again, I will come to that. $name, $1, $3 name, and same thing will be repeated for all the binary operations. For negation, there is a change because all arguments are not present. The first one is not present, but rest of the things are same. Okay. Now, two things are remaining to discuss. One is quad, class quad, and another is this capital plus, what I mentioned. By looking at it, you probably guess that it is going to be some enumeration type, or say some kind of defined statement, something. Yes, it is enumeration type. So here, this is the cal.y, the symbol table, the gentemp, and then the YY error main, there is no change, but remarkably you see that emit function is not here, because emit function was responsible for printing. It is not there. Instead, I am defining one class quad which will help me to generate that string and store that string in an array. Of course, you can make the necessary modification in your previous emit function, and instead of class in C also you can implement. Only thing, instead of print, you need to store the total content which is printing to some array and return that array, which will store in some array of three underscores. Okay, that is possible. Now here in y.tab.h, you do not see any difference. It is the same as the previous one. Next, in the parser.h. So as I mentioned that plus, minus, multiplication, division, unary, minus, copy, those are I am defining as opcode type. They are nothing but the enumeration type. So if you do not know this enumeration, you have to revisit your C or C++ class. So in the enumeration, if since I am mentioning plus equals to 1, so accordingly minus will be assigned as 2, will be assigned as 3, division will be assigned as 4. It is obvious, unless otherwise you explicitly mention them some different value. Okay, otherwise it is not required. So the advantage is that I need not have to carry either the character plus, minus, or explicitly I need not have to spell this plus, minus. Yes, here I will, when I will say plus, minus, I will spell it, then it will take the value 1, 2, etc. That way, you see that the program will also be, and the readability of the program will also increase. If you say use plus, minus, either as a character or as a string, then you have to carry that information. But if you write this plus, minus, then readability will increase. Now what is there in the quad class? It's opcode type of, which is declared here. Next, character star result, argument 1, argument 2, 3 locations, and everything is inside parser.h. Please note it down. Now public, two constructors, quad. So one is opcode type of 1 and 3 addresses for binary operation and for unary operation. Star S now. Okay. And for this copy statement also, I have something for you. And finally, when void print, now you see that it is void print. Going back to the previous slide. What you see in the start statement list that q array I print. So I am calling the function print inside the class. So what is print? Print is basically printing all those opcodes. It is an intelligent way of printing, but in a very straightforward way also you can have your printing. That is absolutely no problem. But it is an intelligent way which says that, okay, so if it is within this range, then it is a binary, because you have to understand that what will be the format for the copy statement, for the binary operation statement, and for the unary operation statement. Okay. Now for the flex specification, absolutely no change here. Okay. And here is one sample run, and this sample run will generate the 3 address code. But only difference probably you noted here is that in the previous case, so when I say a dot out, then after entering this information corresponding to this, say up to this was printed. After then I enter this expression, then corresponding to this up to this was printed. Then I entered this one and corresponding to this up to this was printed. Now what is happening that I entered 3 expressions one after another, and after that all the 3 address codes are generated. So what is the difference? In the previous case, all the temporaries was starting from T00 because each one line was considered as one instance and corresponding to that 3 address code was generated. Now in this case, generation is done after consuming all the statements, and then finally it is printing the 3 address code. So the temporary goes up to T14. Now this is a more like generating the 3 address code for a complete program. Instead of say I got one line, then corresponding to that 3 address code, I got another line corresponding to another 3 address code, and that will create the problem like T00 will occur more than once, T01 may occur more than once that way. Whereas if I have this lazy splitting, then I will I will read the complete source file and then I will convert in the 3 address code, but will print once I will finish reading the source code, then I will print everything. That way all the temporary variables will be different and generation of the machine code as well as the optimization will be very easy for this purpose. Okay. Next, if we add Boolean expression. For the Boolean expression, we have 7 production rules. First one is the OR operation. Second one is the AND operation. Third one is the NOT operation. Bracket is there also. Fifth one is the relational operations where the relation is greater than, less than equals to, greater than equals to, comparison and not equals to. Additionally, I have one true statement, another false statement. So these are the production rules for the Boolean expression grammar. Okay, let us see what we can do. Now, if there is one expression something like a greater than b or c equals to d and not e less than f, then if I draw the tree, then it will be b1, b2 or b3 using that previous production rule. Then under b2 there is if e1 greater than e2, e1 is a, e2 is b. Then this under b3 grossly I can see that this one and this one. So before and operation b5, under b4 c equals to d, then under b5 here not, here within parenthesis e less than f, this there. And if I translate, so first column again indicates the serial number, T1 equals to a greater than b, T2 equals to c equals to d, T3, each and every one I am evaluating first, then I am checking, and finally I am concluding. But you know that by looking at this expression, you will also agree that if a greater than b is true, then I need not have to check anything on the right hand side. See, this is one optimization, isn't it? Because it is an OR function. OR means if you look at the truth table that if one is true, any one is true, then the output will be true. So if A is greater than B, then I need not have to check further. So this is not required, this is not required, this is not required, this is not required. That way I can save a lot of computation time. Also, if say A is not greater than B, then here if I find say C is not equals to D, which is false, which means I need not have to compare E and F and take the negation operation, because in the end both needs to be true. Now under this situation, it is not possible, and this demands that it is the responsibility of the programmer who will decide, it is the responsibility of the programmer who needs to write it correctly, so that I need to do minimum number of operations. But you see that if I can draw this syntax tree in some way, or if I have some statements in such a way during 3 address code generation that I can do that optimization, then the programmer can mostly focus on the logic of the problem and he can write the code. So I am taking the responsibility from the programmer to me, that okay, you write your expression, I will do that analysis during the code generation, and if possible I will do the necessary optimization. Because you know, this is kind of optimization which very much depends on the value of the A and B, C and D. So it is also the run specific or input specific. In one set of input, it may be that A greater than B, and because of that one you need not have to check the rest. In another case it is not, so you have to check the rest. So that provision also needs to be there in your optimization. Okay, so that control flow, if I can make some shortcuts, then that's great. And here is how we can achieve that one. The same thing as I mentioned. So green line indicates the true exit and red indicates false exit. So if A greater than B, then I need not have to check anything, just go to the true state. If A not greater than B, so I am here, then I will check C equals to D. If C equals to D, then I need not have not equals to D, then I need not have to check anything. I will go directly to the false state. Else I will go to the next. Now you see that the number of comparison may reduce based upon the input, and it is not the case that always I need to perform this comparison, then this OR operation, then this AND operation, this comparison, this NOT operation. So everything I did not have to evaluate, because the flow diagram also indicates that one. So what is the best way possible that I can do that one? Okay, so that I am going to do. In order to do that one, here is the situation what I mentioned, that when say there is a go to statement, I kind of confused that where to jump, and I am writing that one at the beginning, that yes, I am confused, I do not know. So first, if A greater than B, go to question mark. I know that it will go to true state, but what is the location of the true statement, that I do not know, so I am giving the question mark. But my flow is to this. Okay, this 106 doesn't come yet because I am at A greater than B. Next, if it is false, then go to some state, that will be my next. Then here again I will compare C equals to D, go to where I do not know, then go to where it will be here, but I do not know at the beginning that what will be the sequence or the serial number for this go to state. Okay, next, if it is true even, then I have to check this E less than F, and if it is true, then where to go to, that if it is true, then definitely this not will give it false, so it will go to the false state, otherwise it will go to the true state. So the flow indicates, but here you see that all are question mark, and as I expected, because I do not know where to jump or where to go, that I will fill by modifying my production rules. But before that, in summary, from the same expression, Boolean expression, what we got is that if a greater than b go to true, from the previous slide I am summarizing here. If it is false, red indicates false exit. Then go to here. If it is false, then since it is an AND operation, so this will go to the false state. If not, then if E less than F, that is true, if it is true, then it will be false, then it will go to the false state. Negation is there, so true exit will go to the false state and false exit will go to the true state. Now you see that number of comparison. So here 1, here 2, here 3, and these are the flows. Okay. To summarize the OR operation, AND operation, and NOT operation. So for the OR operation, you know that if first one is true, no need to check the second one. So I am going to the true state. But if first one is false, red exit, then I need to check the B2, and if it is true, then it will go to the true state. If it is false, then go to the false state. Whereas for B1, so for AND operation, if it is true, then I can go for checking B2, but if it is false, it will directly go to the false state. If B1 is true, then after checking B2, if it is also true, then I will go to the true state. If it is false, then I will go to the false state. For NOT, if it is true, then it will go to the false state. If it is false, then it will go to the true state. Now, specifically for these two, you see that sometimes one test is enough, because from here there is one path to true state. From here there is a one path to the false state. Sometimes one test is enough. Sometimes one test means testing B1 is enough, but sometimes you need to test B2 also. Now you know that I don't know what will be my input. So based upon that one, during the run time, there is a possibility only evaluating the B1 is enough. Sometimes it is not possible. So I will keep both the things open so that whenever it is required to evaluate B2, I will evaluate, and that is my worst case possibility. Otherwise, I will not evaluate B2. So probably, although we are in the IR and shared code generation, but probably you are getting a feel of optimization during compilation process. That it may not be required to evaluate everything, but part of the evaluation is good enough. Because for this OR function, if B1 is true, no need to test the B2 as per the truth table. In case of AND function, if B1 is false, no need to test the B2. As per the truth table, it will be false. Okay, so let us stop here today. So we will continue on the next class. So if you have any question, please let me know. Okay, so if you do not have any questions, so let us stop here. So we will continue to the next class on Monday, but our lab class will be on Thursday. So we will start at 2 p.m. on Thursday. Okay. Thank you very much for your attention.